So good morning, I'm Andrea Maioli. I'm toward the completion of my PhD, and my research aims at enabling a sustainable Internet of Things by improving the reliability and efficiency of batchless devices. Nowadays, there are 14 billion devices that are deployed in the Internet of Things, enabling a variety of smart applications, and this number is expected to grow up to 47 billion in the next few years. And most of these devices are currently using batteries, which have high maintenance costs. They need to be periodically recharged, replaced, and eventually disposed. And this, of course, introduces significant environmental impact. So to address these two problems, researchers want to remove batteries and power batchless devices using only the energy harvested from the environment, which is then stored inside a capacitor that simply acts as energy buffer. So this leads to batchless devices that require almost zero maintenance, with a consequent reduction of maintenance costs, a great long-term sustainability for the system also. However, using only the energy harvested from the environment as the only power source causes devices to experience frequent power failures that introduce several challenges that need to be addressed in order to use these sensors as sustainable sensors for the Internet of Things. So let us simply consider the device behavior at runtime. The device is initially powered off and harvests energy from the environment to recharge its capacitor. When it has sufficient energy, it powers on and starts computing until it has no energy left. And here the device immediately shuts down as it experiences a power failure. And this behavior is repeated for the entire device lifetime. We must consider that these devices are highly resource constrained. They do not have an operating system such as the one of your smartphone or laptop that manage power failures. And this means that whenever the device shuts down due to a power failure, it also loses the state and the results it computed. And as a consequence, in the next power cycle, it will have to restart the computation all over again. And this prevents devices to produce useful results. So to address this problem, the literature required the device to periodically save its state onto a non-volatile memory location, which is persistent across power failures. Then, restoring the saved state from non-volatile memory allowed the device to resume the computation from where the state was saved. So despite this first problem, there are other problems that prevent the batchless devices to be used as a sustainable sensor for the Internet of Things. And there are two main problems that I'm tackling during my PhD, which are computational correctness and energy efficiency. Regarding computational correctness, power failures introduce a new type of bug called intermittent anomalies that essentially corresponds to unexpected behavior that are unattainable in a continuous execution, that is, an execution that lacks any power failure. To give you just an example from my research, let us consider a temperature sensor that measures the room temperature, let's say 20 degrees Celsius. Then the device saves the state and a power failure occurs. While the device is powered off, the temperature raises to 25 degrees. Then the device turns on, restores its state, resume the computation, and at some point it will have to decide whether to turn on an heating element or not. And as the measured temperature is below the considered threshold, the heating element is turned on. However, the actual room temperature is above the considered threshold, and so this represents the heating element should not be turned on, and this represents an anomaly that is essentially an intermittence anomaly caused by the power failure. So to address these problems, during the first part of my PhD, I first focused on identifying a new type of intermittence anomalies that were previously overlooked by the literature and happen whenever accessing non-volatile memory, or, such as in the example, whenever interacting with the environment. I designed a set of techniques to identify where these anomalies may happen, what are their effects, and how to avoid them, and I implemented them into a tool that allowed developers to test the intermittent executions of their programs. Then, a second part of my PhD, I focused on improving the energy efficiency of batchless devices, and this is very important because harvested energy is scarce, limited, and usually unpredictable. This means that whenever the device has energy, we want to extract the best possible computation out of it. However, the two operations required to operate correctly these devices, which are saving the device state and avoiding intermittence anomalies, have a severe negative impact on the device energy consumption. And this is because they usually require the device to execute additional and dedicated instructions, and those instructions also access non-volatile memory, whose accesses are extremely expensive, both in terms of time and energy. So to address this problem, during the second part of my PhD, I designed a set of techniques that allow the device to save the state and to avoid intermittence anomalies efficiently in such a way that does not require to execute dedicated instructions or additional instructions. And this has a reduction of also the non-volatile memory accesses that the device has to perform. I implemented these techniques inside a tool that automatically applies them to any given program for batchless devices, and our results shows that the device energy consumption is reduced by up to 2 orders of magnitude. So this wraps up my research and my presentation. Thank you for your attention, and if you have any question, I'm ready to take them.
So we move now to the second presentation, which is given by Eleonora Darnese, Chimera, a framework for optimizing medical image analysis.